So thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Nicholas Fazio, who will tell us about low overhead magic state circuits with transversal CNOTs. So Nicholas is going to be conferred PhD, I guess next week, very soon, from the University of Sydney for research done on like quantum fault tolerance. His main research interests are in magic state distillation and noise characterization, with a particular focus on applications in near-term quantum devices. So Nicholas, the floor is yours.
Thanks for the introduction, and thanks for having me. Yeah, this work kind of came out with a collaboration with some researchers out of Oxford and UCL, Mark Webster and Zhenyue Tsai. And Mark Webster was a former sort of alumni from the University of Sydney. Now very busy over in UCL, and he's sort of co-first author, and Zhenyue Tsai kind of came up with the idea of this project. I'm very happy to talk about it today. So just to give a kind of broad executive summary of kind of what we achieved, we kind of give some new sort of fault-tolerant magic circuits composed of like CNOT plus T, and that probably what that means will probably be very clear in time. An algorithm for compiling Clifford blocks down to sort of low CNOT depth plus like swaps. And then in sort of using these things, try to sort of like essentially show that we can bring down tech overheads using these techniques, assuming that transversal CNOTs is something that we can do much more easily on the device compared to maybe some other steps. And of course, at any point, if I'm going too fast or if you want to ask a question, just ask them and I'll be very happy to respond. And so just to give some sort of motivation behind sort of the magic states and sort of why these circuits are used and matter, in order to sort of achieve universal quantum computation, be able to sort of implement any sort of unitary to arbitrary precision, we need some kind of universal gate set. And typically Clifford plus T is this gate set that people go for. And a normal sort of way of doing this is generating the Clifford group with S, Hadamard, and CNOTs, or the normal way it's described, and then supplementing it with a non-Clifford T gate. Now, this is all well and good, but one important component is that we need a fault-tolerant universal gate set. And the problem with that is that we do have the Easton-Keneal theorem, which is essentially a no-go theorem, which is that the transversal gate set of a quantum code is not going to be universal in sort of a standard definition of a quantum code. And there's obviously ways that people try to go around this, but the key thing is that this is kind of a fundamental barrier in terms of just utilizing transversal gates in order to sort of make these logical gates in a code fault tolerant. And so you need so you can't use transversal gates to make all of your gates fault tolerant. You need to use some other method as well. The way I kind of think about this is that magic state injection is actually kind of the reason why we can get around this. So instead of thinking about a T gate, we can think about this T state, which is effectively you can apply a T to a plus state. And you can do this sort of adaptive circuit, this magic state injection, where you take the T state as an input, take your computational state, and do this entanglement and sort of adaptive feedback to implement a T gate on an arbitrary computational state. And this kind of maybe feels like you've pushed the goalposts away, but the key thing here is that because there's sort of a T in preparing this state, but the key thing is that we can do this offline in terms of state preparation. So you kind of you exchange fault tolerance in your gate implementation, for fault tolerance in state preparation. And state preparations requires maybe less degrees of freedom to worry about, because you don't have to worry about being able to do it on arbitrary state, like the implementation of T on any arbitrary state in the code space. But I would say it's not a free trade-off, because this adaptive S is kind of a fundamental component. And there's a lot of people that look into the fact that latency has a big, decoding time has a big influence here. And that's something that we consider as well. And so key thing here is that, okay, we do all of our other Clifford gate set transversally using a suitable code. And then using something like magic state distillation, we can prepare really high fidelity magic states. And kind of in the original way that magic state distillation is framed, you take sort of n noisy copies of T, and assuming you have ideal stabilized operations, you can do some sort of a bunch of stabilized operations, which are like Cliffords and Pauli eigenstates and ancillas and so on, to measurements to get less noisy copies, higher fidelity T states. And in essence, sort of magic state cultivation, preparation, zero level distillation, and so on, very much in the same family as the original magic state distillation. But I would say that the key distinction is that they're now being very cognizant of the fact that obviously ideal stabilizers don't exist, right? And being tolerant to the noise that happens at the circuit level and the stabilizers that you're implementing is also important to making sure overheads are low. But many of the sort of techniques in terms of what you look for, in terms of codes of transversal Hadamard or transversal T's, are kind of borrowed from magic state distillation literature. And so in some sense, the T gates are the element that build up these circuits, these magic circuits that we'll have that are either magic state distillation circuits or even just synthesis circuits trying to compose some gate from the high levels of the Clifford hierarchy. And we'll basically take this as like the fundamental block that we'll be building everything out of. And so T-gate is a pi-on-4 rotation about the block sphere along the z-axis, sometimes called the pi-on-8 gate as well as pi-on-4. And this is the kind of convention that I'll also prefer in this case, because thinking about the T-gate in terms of its, decomposing it into Pauli basis is probably going to be the more important way to think about this work. And the reason why is because what we're going to be using is this sort of algebraic object of like phase rotations. And to make it as kind of clear as possible, right, and make the kind of do this notation slide and get it out of the way. The way we're talking about things here is like, suppose you have some multi-qubit Pauli Z, right? You have this bit binary vector, right, which effectively tells you if it's 1, there's a Z on that qubit, and if it's 0, there's no Z on that qubit. And then a phase rotation is to take sort of this Pauli Z rotation and then rotate it some arbitrary theta about that observable. So in terms of how that acts, right, there's some kind of parity between your multi-qubit Z and your computational basis state, and then that determines what computational basis states get some rotation of theta, or 2 theta in this case. So just to give an example, right, if you have binary 1, 1, then that means you're acting on Z on qubit 1 and qubit 2, which is 1 minus 1 minus 1, 1. And then the corresponding phase rotation just does an e to the 2i theta rotation in the same places where the -1 eigenvalue would have been. Does that make sense? I actually can't see that. If I hear nothing, I'll assume yes. And so these are kind of broad algebraic object kind of bring it back a bit, actually, one of the reasons we really want to think about things in this way is because we can decompose various types of non-Clifford operators from the third level of the hierarchy in terms of these things called phase polynomials, which can be one way of essentially figuring out how many T gates do you need to construct one of these gates. So just to give an example, right, the CCZ gate is composed, and when it acts on some arbitrary computational state XYZ, applies a -1 when X, Y, and Z are all 1. And then you could rewrite this -1 in terms of these e to the I pi and 4 rotations, because that's what our T gates are going to compose to give. Going to sort of rotate in your various axes. You can do a similar thing with CS, I on XY, when X and Y are both 1, and you can do it in this way. And then one gate that's going to come up that we use here is this CC minus IZ, which is essentially CCZ times CS dagger. And that's maybe reflected in this polynomial over here. You've got 4xyz minus 2xy. And then this is where sort of the phase polynomial kind of comes into play, because when you think about how you might synthesize this gate and how this circuit is acting on the overall computational state, this T commutes with all the CNOTs, right? It effectively just acts on this Z computational basis state and rotates it by e to the I pi on 4. But this T dagger acts on the modulo addition of Y and Z. So it's kind of acting in this modulo addition basis. This one's acting in a different basis, and same with this one. And what we'll find is when we decompose these polynomials in terms of X, Y, and Z into sort of an equivalent polynomial expressed in terms of modulo addition, we get this. And then we get the composition of our 4 different T gates that can be used to reconstruct this CC minus IY minus IZ. So 1 T acting in Z, and so on. And these exactly correspond to phase polynomials. So this would be a phase polynomial acting on Z, and this one's acting over XZ, and so on. But these aren't just useful for gate synthesis. You see them kind of as a centerpiece in sort of Latinsky style magic state distillation for lattice surgery. But in some sense, they're sort of algebraic. You don't need to think. The lattice surgery is more about how you would implement these phase polynomials. These are just sort of phase polynomials all composing to implement a T at the end. And exactly why that is the case is probably unclear here. So I'll work through it as an example just to give a feel for how these come up. But this is known as the 15-to-1 magic state distillation scheme. And the reason why you might want to do this in this way is because you effectively build in some redundancy such that if some of these phase polynomials fail, you catch the Z errors with these X checks. And you can reduce the sort of the infidelity of your magic state by a cubic after post-selecting. Yeah, and so as said, this is 15-to-1 distillation. It's actually very different to how Bravi Kitaev originally formulated. Keneal actually did another example of 15-to-1 before them. But the kind of modern way people think about magic state distillations is that you sort of encode some logical plus state, which has into a code which has a transversal T. You apply the transversal T gate to apply a logical T, which prepares the logical T state. Then you unencode, you do your stabilizer checks to detect any errors, and then your unencoded magic state should have a higher fidelity. And people usually assume this is done in a code concatenated way so that your stabilizer operators are implemented with high fidelity. So to take this sort of scheme and then relate it back to phase polynomials, right? This is kind of exactly as described. We're encoding into the plus state, applying our transversal T to prepare a logical T state, and then unencoding, measuring out our stabilizers, and then a T state coming out with higher fidelity. Then the T gates that were used to implement it, which are assumed to be implemented with other magic states that are being injected. And so before going into the next slide, I think it helps to think about how conjugating these T states works in terms of this type. There should be an I here, but in terms of this, right? Obviously, CNOTs conjugating an I does nothing. It effectively takes a T state to sort of a multi-qubit phase rotation based on how this step maps.
Nick, can I just interrupt? Can you just with this figure here, like, can you just say where's the code block that's doing the encoding? Like, are we in one level of code or two levels of code at the moment?
So if you would be in two levels in practice, but I don't think many people do this in practice. If you assume that the T states are noisy and everything else is perfect, then you could say this is the first level. The second level only really exists because obviously in practice, these CNOTs are going to be noisy as well.
Yeah. So this is just like one level. So you're going like on the left, you have your physical qubits, and then these control, like these 5 control operations put you in your code, and then you're doing the transversal T's in your code, and then you're decoding these five control operations of the decoding. Is that right? And then
yes.
And then once you've done that, then your 5th qubit is now a T state.
Yes, that's right. But I should highlight here, right, the reason why the CNOTs have to be like ideal here is because sort of almost at any point here, like any errors from these CNOTs are going to directly impact the magic state, and then that kind of ruins the whole thing, right? So the fact that these CNOTs is ideal is kind of something very much taken for granted at this stage.
But like, why is the physical, like, I mean, ignoring the extra layer of coding that's going to happen, in practice, just looking at this, is there a reason why the final unencoded state is a T? Like, I understand you implemented a logical T, but that doesn't mean the physical qubit is going to be a T, right? Like, this is like the property of the code or something that does this?
Like it is possible actually that the I'll need to double check this encoding circuit to sort of answer your question properly, and I can't do that live. But like in essence, right, this encoding circuit should be sort of general in that it would take an arbitrary state to an arbitrary logical code state, which means that the inverse operation, just taking the exact like inverse unitary, should do the opposite and take you from an arbitrary logical state to the corresponding physical state.
Of course. Okay, thank you.
The reason why I hesitate is just because I can't remember if this code block actually does that, or if I take something for granted here. But this does what it says on the tin.
Cool, thank you.
Yeah. And so this is kind of like how people think of 15-to-1 maybe, in terms of like the Reed-Muller code, right, where there's 15 qubit code and you do a transversal T, and you get your cubic improvement because it's 15-1-3. Now to get to this phase polynomial picture, we're going to conjugate all of these T gates to get phase rotation operators, and this is that. It's kind of just qubit by qubit. I'm not going to expect it. It's not important to sort of track this, but you get phase rotations just by conjugating the corresponding Z into a multi-qubit Z. Now, at this stage, though, what's important to notice, and kind of when it comes to phase rotations, we can kind of think of these as like the fundamental building blocks that are actually generating our various non-Clifford operators. So anything, because we're trying to get rid of implementation details. And these CNOTs, for example, are just implementation details of how we're implementing these phase rotations that make up our operator, our total operator. And so what we see, is that the action of these phase rotation operators on a zero state is going to be trivial, right? So actually none of these zero states actually doing anything. They're just implementation details, and we can completely remove them and just look at the top 5 qubits, which gets us to this series of phase rotation operators. And this is the same as what the Latinsky phase rotation operator scheme is. There's some permutations, but it's the same thing. And so sort of given sort of that background, right, what is our work? Sort of given some sequence of phase rotation operators that describe some magic state circuit, we want to sort of take from this kind of abstract form and find a circuit with low T depth and CNOT depth without introducing any ancillary qubits, because this would add sort of extra required space. And then if in a particular architecture, CNOTs can be implemented transversally, this kind of minimizes overheads at a sort of high level. And sort of at a very, again, still speaking at a high level, how do we achieve these overhead improvements? You kind of break the phase rotations into parallelizable collections so that you have a block of CNOTs, a block of T, a block of CNOTs, a block of T. And within each block of CNOTs, we can also further improve it by essentially compiling out various swaps. Now, of course, it's going to be very rare that you actually have 2 CNOTs like this, which you can compile out a swap. But you'll find that sort of in broader blocks of CNOTs, there's more complicated permutations that exist, which are kind of unnecessary that you can pull out. And so pulling out these swaps is kind of where we get a lot of our savings in terms of the CNOT depth. And it's sort of been asked before, why care about T depth when you can kind of have the T's interleaved with the CNOTs? And I do want to say one of the reasons why T depth is important is because of this, of course, this adaptive feedback step, which means that, and based off decoding time and latency, this very much will have an impact on the performance, right? And so if you can, you would prefer to parallelize this so that you don't have consecutive T's in a row where you have to wait for this time each time, because you can't keep going with your computation until you've applied the appropriate feedback. But so one of the main examples that we sort of look at is this 832, which was developed by Cody Jones to essentially make a CCZ that's tolerant to any one T fault. So it's error detecting, and it reduces it to P squared. And Earl T. Campbell has a blog describing this as the smallest 3D color code. So I would suggest reading that if you're not familiar. That's really good. And essentially, it sort of works in this way where, as we sort of discussed before, the CCIZs can be synthesized in terms of 4 T gates or 4 phase rotation operators. And then if you have 2 CCIZs like this, you can imagine the CS cancels out with the CS dagger of this one, so that this is effectively 2 CCZs. And then if you conjugate a CCZ by CNOTs, then you get a CCZZ, which is just 2 CCZs. And so then overall, you get 3 CCZs here, but 2 cancel out, and you get 1 CCZ. But the reason why you want to do it like this is that if there's some error in the CCIZ, which always manifests on the target qubit, then you can detect it using this CNOT check. And then this is also shown over here, but now sort of compiled in terms of T gates on sort of extra ancillary qubits. Does that make sense? And technically there should be a CNOT over here as well, but that's just been, that acts trivially at the beginning, so that's been removed. Yes. So let's take this as an example and work through it, just sort of taking the algorithm as given and then just see the sort of steps of our method. So here is the set of phase operations that we want to optimize that implement a CCZ. And that's just taken from this previous step, and we've just conjugated the sort of red group and blue group of T gates to give the corresponding phase operators. And here acting on the numbers at the top corresponding to the ancillary qubit number. Then we're going to compile it down into each, we've rearranged these phase rotation operators into sort of parallelizable blocks, and how we can tell if they're parallelizable or not, we'll talk about in a moment, but it's effectively that they just have to be linearly independent. And then you can decompose this into a CNOT block that gets you basically from the phase rotation basis into the T, like the computational basis, implement the relevant T gates, sorry, and then get out of that basis back to normal by doing the inverse of this, and then the same thing for the other thing. And you can take these CNOT blocks and compose them together. And so then what you get from this step is you get a CNOT block, T, CNOT block, T, CNOT block. And then from there, sort of hand wave algorithm comes in, and you compile into CNOTs and permutations, and you kind of pull all the permutations through to the beginning. In this case, they all cancel. That doesn't have to happen, but in this case, the wires just happen to untangle such that there's no permutation at the beginning. And the reason why we're bringing it to beginning is that, and you also would prefer to have CNOTs at the beginning as much as possible, is that if we act these on plus states, all the swaps and all of the CNOTs just are all trivial, such that you can write this circuit as input magic states, CNOT block, and then from then on, every T block has to be actual Ts, and then more CNOTs and so on. So overall, this is an identity. And yeah, this is our sort of final circuit in this case. Essentially just compiling out X's from these T dagger states and T daggers, just to make everything nice and clean. And this is what we get. And so in this case, it's 1, 2, 3 CNOT layers, a layer of T's, and then 2 more CNOT layers. So how does the CNOT compilation actually work? So these CNOT blocks actually really straightforward when representing them sort of in this symplectic form, which is kind of like essentially thinking of these operators in terms of like Gottesman-Keneal style representation. And so these CNOT operators we can define in terms of various column vectors U. Right? In each column vector, each column corresponds to how the first computational state maps to under the action of the CNOT. So like let's say 1, 0, 0, 0, 0 will get mapped to U1, 0, 1, 0, 0, 0 will get mapped to U2, and so on and so forth. And that's how this sort of CNOT block acts on the computational basis states. And then in the symplectic form, this U matrix is exactly the same thing. U on the Z, and then also the sort of transpose inverse on the X. And this CNOT basis effectively corresponds to the phase rotation basis as well. So suppose we have some products of phase rotation operators, so some theta I, ui. We can directly map this onto a bunch of product of single qubit phase rotations by conjugating by these CNOT blocks. And so at this is just general statement, right? This does have to be T rotations. It can be arbitrary phase rotations as well. And then once you've got your CNOT blocks, the idea is to sort of compile your CNOT block down one CNOT by one CNOT until there is only a permutation matrix remaining in the symplectic form. And a permutation matrix in the symplectic form is also a permutation of the qubits. And so I'm not going to go through the algorithm, but like in detail, but like effectively sort of you take this binary matrix U as an input, and then at each step, we use a greedy algorithm. So at each step, you apply the transversal CNOT operation, which will minimize the sum of the of your binary matrix until eventually the sum gets to n, in which case you know that it's a permutation matrix, and then you're done. You have a permutation matrix and then your corresponding list of CNOT operators. Yeah, and so, okay, I'll hurry up a little bit. So here's one example for the T-gate, like the 1513 scheme, run through sort of this method. Here's the sort of grouping of the phase rotation operators, and then CNOT block T, CNOT block T, CNOT. I think this is 11, CNOT depth 11. I probably should have that on the slide. And then here's this sort of fault-tolerant CS, which is composed of 12 phased rotations. And then this gets compiled down to the same structure, 1, 2, 3, 4, 5 CNOT depth, and then 3 T depth. And then, yes, of course, this is kind of as we had before, right? Starting with something like this to get your phase rotations, and then compiling it down to something like this. And so kind of as a broad sort of comment, right, the idea was that the reason why we want to actually sort of get in this form is that if we have an architecture where transversal CNOTs are actually doable and we don't need to go through lattice surgery and sort of do our stabilizer checks d times, right? Then we can potentially have sort of lower overhead on performing these kind of schemes. And so this is kind of the scheme written out with the full injection written out as well. And it may seem a bit wasteful that these magic states are being left idle for so long, but it's important to remember that the magic states that will be coming in will be much higher in fidelity or lower fidelity than the fidelity of the gates that we'll be operating with. Because with these schemes, this like fault-tolerant CCZs, we're assuming that the T states coming in will be more noisy. And there's reasons you want to do this because there's obviously overheads with requiring more and more post-selection and more discarding when you want to get to T states of higher and higher fidelity, right? And if what you want in the end is a CCZ, maybe you don't need to get to a T state as high a fidelity. You can run it through something like this and then get a higher fidelity CCZ at the level of your computation. And so although these T states are being left idle, the amount of idling error is almost insignificant compared to the actual T state infidelity. and that idling error will also get improved on each respective state. And so here, kind of write a rough space-time volume. I would say that it is a little bit optimistic in the sense that it's treating this fifth step as easy as the other six. And this has been something we've kind of done in revision, and we need to update the paper soon on the archive. But this fifth step is very much a vital step in terms of like both the time overhead, but also if there's errors that are occurring during sort of latency, this builds up and contributes to the overall fidelity of the CCZ state as well. And that's something we do comment on, but we've also added some extra stuff in the appendix. But the key thing here is that even in the worst case for this adaptive feedback, where this is, let's say, D, this takes sort of D amount of logical time steps, then that's only like 1D plus constant factors. And typically the volume is many multiples of D. And so this still ends up, even in that case, it still ends up being low overhead. And so, yes, thinking back to how these schemes work, right, we're assuming that we're working at the logical level here. And so when talking about the sort of logical noise, the memory errors that are accumulating while we're going throughout this process, any sort of logical error at the end here will directly impact the infidelity of our CCZ. We're kind of inherently assuming that we're at the level of that the computation is taking place at, and that these, really this should be PT is much greater than PL, right, that we have some much more noisy magic state coming in, which is then being improved in terms of the final infidelity of the CCZ. And so this was the original figure that I gave in the paper. And in hindsight, I realized it doesn't really have a great takeaway, but I'm still going to talk to it because it's the one that's publicly available. So what you see here is that there's this inherent flaw associated with the memory error rate. And that's kind of expected, right? Because at every single time step, any logical error that accrues is more or less going to contribute to the final infidelity of CCZ. That's just limited by how you're doing, like how big your code patch is and so on. But then you have some much higher rate in which your T states, like much more noisy T states, right? And they get improved and approach this flaw such that you get improved CCZ infidelity compared to the T states itself. And there's this question of maybe what's, given some flaw, what's the ideal sort of magic state infidelity you should aim for before using something protocol like this. And originally we sort of estimated about 0.7 square root PL. This will become a little bit more easier to understand on the next slide. But coming back to the sort of importance of the adaptive S feedback, this flaw actually scales with the amount of time it takes to decode. And so here we talk in terms of logical time steps, right? So this T decode is referring to the sort of number of, the corresponding time of the number of logical gates that you could have implemented that have gone by before you were able to decode and apply your logical or your S feedback. And for each time step that goes by, you accrue more and more memory errors that affect the final CCZ infidelity. I do argue, however, that this is also true for normal CCZ synthesis, let alone scintillation, because you will need some adaptive T feedback regardless. So in some sense, we're doing no worse than normal synthesis in terms of the infidelity, except for the fact that we're also improving the fidelity of the T state to the final CCZ. And so this is a more recent figure that probably shows things a little bit more clearly, which is so you have some CCZ infidelity at the end and your T infidelity going in. And so you have some regime in which if your T states are really noisy, this scheme will improve things up until you reach the floor for the actual memory error. And so this red dotted line is effectively what was being described as 0.7 square root PL. This one's actually 0.4, but for the sake of the consistency across slides, that's what I'm talking about. And so you can see that if you have some scheme that's actually where the magic state is at this sort of infidelity, it's actually sufficient to just run this, and then you will get a CCZ of fidelity that is at the same level as your logical error rate. And so you don't need to improve your T states any further before compiling your CCZ. You can just run this over top. And so just to kind of go through all that again, in terms of what we did, right? The main idea is that we've taken circuits for distillation and turned them into sort of low depth in terms of CNOTs and Ts to make use of the fact that these CNOTs are cheap on some architecture. We've got this CNOT compilation algorithm that works by factoring out swaps. In other cases where swaps are kind of free due to the particular, or maybe if you have some shuttling constraints, this may be useful. You might also look for particular types of permutations. CNOTs are obviously in general not free. And maybe one sort of more open question, right, is that this is only considering synthesis for CNOT plus T, not Clifford plus T, which is obviously the more universal gate set. Triorthogonal schemes and magic circuits, it's kind of, as we describe them in terms of phase polynomials, these are kind of inherently CNOT plus T, actually, not Clifford plus T. But so sufficient to cover most of them, basically. It'd be interesting to sort of take this kind of idea of composing things further than just sort of this CSS style codes into more general sort of stabilizer codes. My co-author, Mark Webster, did some later work in terms of synthesis, which stemmed from this work. So if you're interested in that direction as well, I would suggest checking out that later paper. Any questions?
Oh, okay. All right. Yeah. So if anyone has questions, please feel free to just unmute and ask them now. Yeah. Okay. Thank you for a very informative talk. Can I ask so when you do the this, you go from the phase rotation operators, right? And then you say you can compile or get it into these blocks of CNOTs and Ts.
Mm-hmm.
Is this something that like you would know exactly how to do this, or because I imagine that maybe this is not unique and you can do this in many ways. And does it matter how you do it, or is it essentially unique?
So there are some degrees of freedom in terms of
I suppose at at very high level, what I'm asking is so once you do this kind of compilation, how do you know that you cannot do better than what you have done?
So
or in some sense, yeah.
Oh, sorry, you keep going. Sorry.
Yeah, no, I mean, I just wanted to say, how do you know whether you can do, is it possible that you might be able to do better if you maybe choose the blocks differently? I don't know.
Yeah, so choosing the blocks differently is obviously a big difference, can lead to some differences. Here, there's so few phase rotation operators that you can kind of just globally go over them and you can check. I think that the question of how can you know if some particular synthesis is optimal, it's very hard. I don't know what computational level of complexity it is, but it's very difficult. As for the CNOT blocks being unique, they are unique up to some kind of like irrelevant, well, not like to some like flipping factors, basically, like Z and X, like single qubit Z and X operators. But that's because we're defining the whole basis change in terms of one computational basis to sort of like a parity basis. Everything else kind of comes into, but then the question after that is, how do we actually compile this sort of abstract CNOT block, which doesn't tell you how it's composed of CNOTs, into actually something that's like a circuit. Yeah. Does that answer your question?
Yeah, I think it's fine. Like, yeah. There's no like simple answer to it, I suppose.
Because, for example, you could, like, one of the things that we compile out of this, for example, is like X gates. You could also get from this basis into this basis if you compiled X's into the CNOT block. But the fundamental thing here is that we're assuming that this block is only composed of CNOTs, right? And then because of that assumption, that's what makes it unique, basically.
Yeah, okay, all right. Yeah, I will let other people ask their questions. Yeah, I'm not seeing anyone asking questions. Like maybe I just a quick follow-up. So when you do yeah, I understand like this algorithm for the CNOT, like where you try to get to the permutation, I think is what you were saying. Yeah. So here, I guess like your algorithm will always be able to do this for you. So you don't need to worry about like, again, like being able to do it better. Like once you get to the permutation, then you know you're essentially optimal in that sense, right? Okay.
So there is potential further optimizations, because the thing that the key step is that we're doing sort of a greedy algorithm at each step. So we're choosing making a choice of CNOTs, which will reduce the sum of the symplectic matrix by the most amount. And this works really well. It's basically, it's close to optimal, but potentially there can be some further improvements. And that was the kind of stuff that my co-author Mark investigated more, and he's got some follow-up work on that. The reducing it down to the permutation matrix. There was another point that I wanted to address that it's now slipped my mind. Oh yes, sorry. One thing to make sure that this algorithm works, though, is you have to make sure that the group of collection of phase operators that you choose is actually parallelizable. It's not guaranteed that you're able to. It's actually possible to write a CNOT block, transversal T CNOT block as this. Sometimes you might be forced to implement a T on a particular qubit, or you might have to do them in succession, like one T and then a CNOT and then another T, for example. And essentially the condition to know that this is true is that this matrix U has to be linearly independent. Yeah. And then that means that it will be parallelizable, and then you can reduce down to this permutation matrix.